Okay, so welcome to the 29th video in the Discrete Structure series, and this video is going to be the start of a new chapter, Induction and Recursion. So in this particular video, we'll be introducing the idea of mathematical induction, and we'll try to reason why a proof using mathematical induction is valid, and then we'll spend the remainder of the video solving 8 numerical problems in mathematical induction. I have collected a few questions from different categories, so we'll be looking at them and solving them. So let us begin our discussion with the basics about the process of induction. And we're going to use the famous domino example to demonstrate the process of induction. So it goes like this. Consider that I have a pile of infinite dominoes. I'm sure all of us must have heard about dominoes, and even though we haven't heard the word, we must have spent some time in our childhood doing this. So we can imagine all of these as being bricks that are placed closely together. And the process of induction just mentions the fact that if I were to cause this first domino to fall, that would cause all the other subsequent dominoes to fall. Before we try to look into it mathematically, let's ensure that we are on the same page about what happens when I knock this first domino. The moment the first domino is knocked, it causes the second domino to knock, and then the chain continues until all of the dominoes in this arrangement fall. And if I want to know how this process relates to mathematics and proof, let me try to number these dominoes. I want to call this 1, 2, 3 and so on. I can rephrase my earlier statement saying that if domino number 1 falls, domino number 2 will fall and so on. So essentially I have proven this fact of falling of dominoes for all natural numbers n. And it turns out that this falling of dominoes is just one example. The exact same reasoning process can be used to prove many facts for all natural numbers n. So let us start by trying to figure out what it takes to cause all dominoes to fall. And from our earlier discussion, it seems like I need to do two things in order to cause all dominoes to fall. The first thing that I need to do is to knock over the first domino. And is this really enough? What if the second domino is far away and the first domino doesn't hit it when knocked? And this argument is not just for the first two dominoes. For any two consecutive dominoes that I choose from here, we need to be able to guarantee that a given domino will knock the domino next to it. So I want to establish that every domino, if knocked, will knock the domino next to it. And given these two facts, I can successfully conclude that all dominoes fall. And now let's try to mention the same thing with our propositional logic toolkit. So I need to prove any proposition Pn like this all dominoes fall for all natural numbers n. And the process of induction requires me to carry out two steps. I need to start by saying that the first domino must be knocked over, that the first domino must fall, and that is equivalent to saying P1. And then I have to say for every domino, if it is knocked, it will knock over the next domino. So that is the same as saying for all dominoes in the index k, knocking that domino will knock over the next domino. Next we'll dive into problems, and this concept will become even more clear, but before that I want to touch a little bit on why induction works. Let me grab a little bit of space. So there is a formal proof of the process of induction, and that involves the Weil ordering property, and I've tried to compile that proof into one sentence here. You can't have a first instance of something false if the thing before it ensures it to be true. And the main highlight of this statement is this part, first instance of something. This refers to the Weil ordering property, and it simply suggests that every set of positive numbers has a least element. So let's have this set of positive numbers. And the Weil ordering property suggests that since all the numbers in this set are positive, there exists a least element. In this case, my least element is a 2. And I know this sounds like the most simple and obvious thing in the world to say, but think about it. If this was an infinite set, it would still have a least element provided that all of those numbers were positive. But if you consider a potentially infinite set with negative numbers, you are not guaranteed to find a least element. So the Weil ordering property says that this set of natural numbers 1, 2, 3 up to n has a least element, and that is 1. And we should appreciate it because it mentions positive numbers. If I were to consider the sequence -1, -2, -3 and it went all the way to infinity, this wouldn't have a least element. Because higher I went on my sequence, smaller the number would get. So how can we use the Weil ordering property to show that mathematical induction works? So the thought process goes like this. The claim is that all dominoes fall, and then let's assume that mathematical induction doesn't work. Okay, all dominoes don't fall. Now if all dominoes didn't fall, I can collect which dominoes didn't fall in a set. So let's assume because mathematical induction is wrong, domino number 57, 53 and 55 didn't fall. Now I know from my Weil ordering property that this set has a least element, and my least element here is 53. Now since 53 is the least domino that didn't fall, I can conclude that domino number 52 actually fell. And that is where the well ordering property comes into play. 53 is the least domino that didn't fall, means every domino before 53 fell. And so did 52. But now this is interesting. This suggests that every time domino 52 falls, domino number 53 must also fall. Because if mathematical induction doesn't work, it shouldn't work despite this being true. And so we can conclude that there is no way 53 didn't fall. So 53 actually fell. So I can remove 53 from this set of the dominoes that didn't fall. And now I can apply the same logic on the reduced set. So ultimately, I'm going to be able to prove that this set is empty and there is not a single domino that didn't fall. So you can't find the first instance of something false if the thing before it ensures it to be true. And by the way, this logic of looking one domino before does not work for the first domino. But you can never put this first domino in this set because the fact that the first domino falls is established in here. And therefore, in my well ordering claim, I never have to go from 1 to 0. I never have to have the 0th domino cause the first domino to fall. So we'll be looking into the topics of well ordering and strong induction separately in our upcoming videos. But for now, let us move on to the problem section of our video today. All of the questions that we do today are going to be proved using mathematical induction. So I'll be doing the first question completely formally, showing you exactly what steps need to be done. And for the subsequent questions, we will solve them and demonstrate the approach, but will not be as thorough as in this solution. So the first question requires me to prove that the sum 1, 2, 3 and so on up to n is given by this expression n into n plus 1 divided by 2. So I have intentionally chosen an easy question to start, but we'll be looking at questions from different categories. This one is from sequences. We'll look into a few inequality questions, a few questions from divisibility, and also a couple of questions from sets. So a lot to do. Let's get on to the solution. So the first thing that you want to do when giving a formal proof is to restate the hypothesis using a propositional function. So let me write my hypothesis, and I want to mention a propositional function Pn such that 1 plus 2 plus 3 up to n is given by n times n plus 1 by 2. Now this step does look repetitive, but using a propositional function allows me to generate a family of propositions. For example, P of 3 would mean 1 plus 2 plus 3 is equals to 3 into 3 plus 1 by 2. And that would be a proposition that you could verify and check whether it's true or false. So the hypothesis is a propositional function on the domain of the set of natural numbers, and for each natural number, it will give back the corresponding proposition. So the next step in induction is the inductive basis. Let's just call this the basis step. And this step is analogous to requiring the first domino to fall. And we saw that mathematically it was equivalent to proving the hypothesis P of 1. So let me evaluate the proposition corresponding to P of 1. It would simply say that 1 equals 1 times 1 plus 1 divided by 2. And this 2 will cancel out. This gives me 1 is equals to a 1, which is an identity. And I can conclude P1 is true. So the next thing that I want to do is to prove that the implication Pk implies Pk plus 1 is true. And we do that by guaranteeing every time Pk happens, Pk plus 1 is bound to happen. So if we can assume that Pk is true and then use that assumption to somehow prove that Pk plus 1 is also true, this implication will be validated. Therefore, the next thing that I want to do is to build my inductive premise. And the inductive premise is the statement Pk is true. So what does it mean for Pk to be true? This implies that the sum from 1 to k is k times k plus 1 by 2. Alright, now the final step in my induction is to use my inductive premise to prove that Pk plus 1 is also true. So let me get a little bit of space. So my final step is gonna be my actual induction. And my induction step requires me to prove that Pk plus 1 is true. The nature of the hypothesis will determine what approach you should use in order to prove that Pk plus 1 is true. But it can be guaranteed that for all problems, in order to prove that Pk plus 1 is true, you have to use the fact that Pk is true. There will be no way to prove the induction without the inductive premise. And you should use that as a hint. Whether you are doing an algebraic simplification or a logical reasoning in your induction, you will use the premise one way or another. So let us get on with the proof. So let me rephrase the statement that I need to prove. What does it mean to say that Pk plus 1 is true? It simply means that the sum from 1 up to k plus 1 will also follow the same pattern. So I can rephrase this as this sum up to k plus 1, and this should be equal to whatever this expression is if I replace a k with a k plus 1. And that is going to be a k plus 1. I'm just going to say in this way k plus 1 divided by 2. So this is the expression that I need to prove. And if I can prove this is true by using this, my induction is complete. So let's try to make this proof. I want to start from the left hand side. And I know it is the sum from 1 to k plus 1. Now we know we need to use this, and here it's easy to do that. There is the sum from 1 to k, which I can replace with this value, and that gives me k times k plus 1 divided by 2, and then I have a k plus 1 again, And now it is all about simplification. I want to take a k plus 1 common, and then this is going to leave a k plus 2. When I take the LCM, and you can see this is the same as this expression. So we successfully used our inductive premise in order to prove our induction. Okay, so next we'll go over a few other problems, and like I said, we won't be spending much time doing them formally, but we'll look into the approach and the solution for each of them. So look at this another question from sequences. I have this 1 plus 3 plus 5 and all the odd number added together is going to be n squared. And the reason this is slightly different from our last question is because we don't know the general term. Last sequence was just 1 plus 2 plus 3, so the general term would be n. But if the question only gives you something like this, you need to be able to identify the general terms. How many terms am I actually adding in order to reach n square is the main question. So the general term in this case is just given by 2n minus 1. When I plug n is equals to 1, I get this value, n is equals to 2 gives me this, and so on. And the way you figure that out is by using the arithmetic sequence formula. Not going over that now, but you want to rephrase this as 1 plus 3 plus 5 up to 2n minus 1, and this is equal to n squared. And so we already saw that the basis step for 1 is true. So your hypothesis will just look like 1 plus 3 plus 5 all the way up to 2k minus 1 is going to be k squared. Okay, so this is what I'm going to assume. And the same thing should also be true when I take one more term in this sequence, and that should give me k plus 1 squared. So what I'll need to prove is all of this. This is the same thing. And what is going to be the next term after this if I were to add 1? We can see that each term is just 2 added to the previous term. So I have this entire thing here, and then I have a plus, and I can add 2 to this term in order to get a 2k plus 1. So this is my extra term, and presumably this sum should be equal to k plus 1 squared. But this is something that I will not know, and I need to prove. And I can do that by using my hypothesis. I know that this entire sum is just k squared. So I can write this as k squared plus 2k plus 1. And then you can see this is k plus 1 squared. Just applying the square formula expands into this expression. And if you did not like my idea of adding 2 to this term in order to reach this term, you can also simply replace the k with a k plus 1. So if you do that, you get 2 times k plus 1 minus 1, which also gives you 2k plus 1 like you need. So it's all about having the right concept and mindset. These questions are really easy. Let's move on to the next one. So this question is also from sequences. I want to be able to show that 1 plus 2 plus 2 is squared, and all those powers of 2 added together up to n gives 2 power n plus 1 minus 1. So this time we'll jump our steps even more. You can just test for 0. This is just going to be 1. 2 minus 1 is 1, and that is the first term. And you know that our inductive premise is just going to be the same statement, but n replaced with a k. So my inductive premise or my assumption will look like this. And then I'll need to prove the same thing for k plus 1, which will be analogous to writing this. And this should hopefully be equal to whatever I get by substituting k plus 1. So when I substitute a k plus 1, this is what I get. So I need to prove this is equal to this. So I can again do the same thing, and this will repeat all over sequences. All of this thing is equal to this term. So this sum will become 2 to the power k plus 1 minus 1, substituting from here, plus 2 to the power k plus 1. So this is just x plus x, that is just 2 times x, 2 times 2 to the power k plus 1 minus 1. And you should recall the laws of indices from childhood. I have a power 1 here and a k plus 1 here. So these powers will add. I'll get 2 to the power k plus 2 minus 1, which is the expression that I need here. So I've done the same thing here. By assuming it for k, I'm able to prove it for k plus 1. Alright, next we'll look at a couple of problems from inequalities. I want to look at this problem, n less than 2 power n. So if I plug a n is equals to 1, I can see that 1 is less than 2 to the power 1. The basis is pretty simple, and in my inductive premise, I'm going to assume that k is less than 2k is true. And I need to somehow be able to prove that the fact is also true for k plus 1. So I need to prove that k plus 1 is also less than 2 to the power k plus 1. And in this case, I want to start this way. I want to start by writing k is less than 2 to the power k, which is my assumption. And then my objective is to be able to compare k plus 1 to something. So I'm going to add 1 to this equation, and I'm going to note that that is going to be k plus 1 is less than 2 to the power k plus 1. And now I can say since k plus 1 is less than 2 to the power k plus 1, it is definitely less than 2 to the power k plus 2 to the power k. So I substituted a 1 with 2 to the power k, which is bigger value than 1. Since my k is at least 1 or more, I can guarantee that 2 to the power k is always greater than 1. Therefore, this value will be less than this value. So I could in fact replace this 1 with anything that is greater than 1, but I choose to do 2 to the power k because that takes me towards my expression 2 to the power k plus 1. All I need to do is to show that k plus 1 is less than 2 to the power k plus 1. And now I want to write equals 2 to the power k times 2, the same thing as we did before. And remember not to write less than here the sign that you write always corresponds to the previous expression. So I'm writing greater than because I know this is greater than the previous expression, but what I'm writing here is actually equal to the former expression. So I want to write equal to, and this is going to be equal to 2 to the power k plus 1. So then what is the relationship between k plus 1 and 2 to the power k plus 1? I can say using this inequality or this one that k plus 1 is strictly less than 2 to the power k plus 1, which is the same as this expression. Okay, there's going to be one more question about inequalities. I'm just going to put the question here. It says that 2 to the power n is less than n factorial. So I'll give you guys hint. 2 to the power n is just 2 multiplied with itself n times. So let's say if n is 100, it is just 2 into 2 into 2 happening 100 times. But in n factorial, each time I'm multiplying with a bigger number. When I take 100 factorial, I have 100 in my product and I have into 99, into 98. So the number of product in both of these terms are the same, but this is the product of only 2's and this is the product of all numbers below n. So this is definitely going to be much bigger than this. And in this question also, you are going to have to find a clever way to make a substitution in order to find the inequality that you need. So you'll need to prove that 2 to the power k plus 1 is less than k plus 1 factorial, given that it works for k, of course. So let me just make this into a k. So this will be my inductive step. So if I know that 2 to the power k is less than k factorial, I need to be able to prove this. And I'll give you a hint. In this proof, you'll be using the fact that 2 is less than k plus 1. In here, we used 1 less than 2 to the power k, correct? We used 2 to the power k and substituted 1 with 2 to the power k. So in this problem, we are going to use this identity. You're going to replace a 2 with a k plus 1. Okay, so let's move on to the next class of problems, divisibility problems. Prove that n cube minus n is divisible by 3. So putting n is equals to 1, I get 1 minus 1 is equals to 0 and 3 divides 0. This is fine. You could try a few more just to verify for yourself. Try plugging in 1, 2 and 3. All of them will be divisible by 3. So let's move on to my inductive premise. I'm going to assume that k cube minus k is divisible by 3. And I want to be able to show that k plus 1 whole cubed minus k plus 1 is also something divisible by 3. So we can just expand to show that this is just going to be k cubed plus 3k squared plus 3k plus 1. And I'm just going to write minus k minus 1 expanding in. And one hint, when I'm proving a divisibility by 3, I want to collect all terms that are a multiple of 3 and take 3 common so that that term is automatically divisible by 3. So let me write this as 3 times k squared plus k. I have taken these two expressions. So plus 1 and minus 1 goes away and what remains is k cube minus k. So I can write plus k cube minus k. So you can now look into this expression. This first part being a multiple of 3 is automatically divisible by 3. And this second expression is divisible by 3 because of my inductive premise. And we know that any linear combination of multiples of 3 is also a multiple of 3. So when I do 3 times this plus add multiple of 3, this whole thing is also going to be a multiple of 3. And that is exactly going to be our conclusion. And this is going to be our last step. I want to mention one another question for you guys about divisibility. Prove that this expression 7 raised to the power n plus 2 plus 8 raised to the power 2n plus 1 is divisible by 57. So this question is also not that tough, to be honest. Only the numbers are kind of large. So just start by assuming this expression for k and write the equivalent expression by replacing k with a k plus 1. And then you want to split the powers. You want to do something like a to the power of b plus c is equal to a to the power b times a to the power c. And the reason you're going to want to do that is because after you change this n into a n plus 1 or k into a k plus 1 for your inductive step, this is not going to be 2n plus 1 anymore. And this is not going to be n plus 2 anymore. But in order to use your inductive premise, you'll still need 8 to the power 2n plus 1 plus 7 to the power n plus 2. So in order to get that expression, you want to split the powers and do some algebra. And like I said, this is not that tough. So I'll move on to the last question of the day. And this question comes from set theory. Prove that any set with n elements has 2 to the power n subsets. And this could also be rephrased as power set has 2 power n subsets. And we have already dived into this topic in our discussion of sets, and I also offered a proof that used binary counting. But here we are going to achieve the proof using mathematical induction. And let me show you our reasoning process behind this problem because the actual solution is going to be quite simple. So let's say I start with a set that is empty. Now this set has no elements and this whole thing will have only one subset, the subset containing the empty set. So when I have 0 elements in my set, I have 2 to the power 0 is equals to 1 elements in my power set. Now let's say I introduce one member A into my set. Now my set looks like this. And now we have 2 possible subsets. The empty set is already existent and then I have a subset called A. Let me do one more iteration to make the point completely clear. Let's say I have another element B coming in and now my set has A and B. So I know that at this time I'm going to have 4 subsets. So let me list them. One is going to be empty. I'm just going to write A, and I'm going to write B and A comma B. So these 4 are my subsets, and it checks out. I have 2 elements and 2 to the power 2 is 4. The reason I'm writing this is to show you the process of induction, because in induction, each step depends on the validity of the previous step. I need to be able to say that having one element creates 2 subsets, and because of that, having one more element causes 4 subsets. So I need to create the dependency with the previous set of subsets. So here is the idea. The first statement I don't have to prove because it is my inductive basis. And I want you to observe that each time we create a new power set, it has exactly double the elements of the previous power set. And the more important fact is how the new sets are obtained. So in my very first power set, I have one empty set here and it is interacting with this element A. Okay, and this is going to be the pattern. Every element in my power set is going to interact with my new element, and there are going to be 2 possibilities. So I'm going to create a new subset without including A. That's going to be one possibility. And when I do that, it's going to be exactly the same set that I copied from. And I'm going to build another subset by combining everything that I had and also include A. So each element in my previous power set will give 2 children. One child will be the same as it, but the idea is that I'm not including my element. And another child will arrive which also has the same element but the extra A. And if that is confusing at all, it will be extremely clear when we look this transition. So in this case, I have empty and A. And then a new character B has come in. So the empty will first interact with B. I'll get one subset by including B and one by not including B. When I do not include B in my empty set, I just get the empty set. It is here. And when I include a B in here, I get this set. These 2 are covered. And now the same thing goes between this set and my new element B. When I do not include B, I just have the same thing, A, which is here. And when I choose to include the B on this set, I have a set containing A and B, which is my set here. And we can keep reasoning in the same process. If I were to introduce one more element called C, each of these 4 sets will give rise to 2 more sets. One by including C, one by not including C. So this is the fact that we'll use in our inductive proof. We'll use the fact that each subset of the lower power will give rise to 2 new subsets when we move one power higher. Alright, like I said, the actual proof is quite simple. We can start with a couple of basic steps. I can say that a set with 0 elements has 1 subset and the set with 1 element has 2 subsets, like we saw here. And then I can assume that a set with k elements has 2 to the power k subsets, and this will be my inductive premise and my assumption. And based on this whole reasoning, when I get to my k plus 1th step, that is like adding one more item to my set, I know that each of these subsets will give rise to 2 subsets each. So on the k plus 1th iteration, I'm going to have 2 times 2 to the power k subsets, which is also equal to 2 to the power k plus 1. So by assuming that a set with k elements has 2 to the power k subsets, I'm able to prove using an induction that a set with k plus 1 elements has 2 to the power k plus 1 subsets. Okay, so that concludes the discussion for this video. We'll start next video with a look at well ordering and mathematical induction. So I'll see you guys tomorrow with the next one. Have a good day and bye.